last two lectures we talked about recursion, and we saw that several problems can be solved very easily and very elegantly using recursion. And in the last lecture we saw how recursion actually works and what happens at runtime when a recursive function executes and so on. So in today's lecture we'll talk about how and when not to use recursion, and we'll see that in many cases recursion is not appropriate, and also in many cases if we carelessly use recursion, we can actually end up with extremely inefficient programs. We'll also introduce some notation for analyzing the performance of programs, which is very important to understand, because our programs should not just work, but we should also try to make them as efficient as possible. Okay, so as we have already seen, recursive algorithms for many problems are much simpler and more natural than iterative solutions, and we have seen a number of examples in the last two lectures. But when we discussed how a recursive function works, you would recall that when the number of function calls that happens is very large depending on the depth of the recursion, and each function call and return has a substantial overhead, because the return address and the local variables etc. have to be space for local variables, and return address has to be created etc. The parameters have to be initialized, and so on and so forth. And this overhead can become substantial in certain cases, especially if the recursion is very deep. So and also in terms of usage of memory, recursion is more expensive because we have to create a stack frame for all the simultaneous invocations of the recursive function. So there is this trade-off between using recursion and writing an equivalent non-recursive or an iterative function for solving the same problem. So the ideal solution is that where the problem is very simple and the non-recursive solution can be implemented as well as understood easily, then we should always prefer not using recursion, because recursion, as we have seen, has a substantial overhead. However, in certain cases the problem itself may be very difficult to solve, or the solution may be very difficult to understand if recursion is not used. For example, the Tower of Hanoi problem that we saw last time, and in such cases certainly we should use recursion. But for problems such as factorial and GCD, which can be easily solved and the solution can be easily understood, even if it is not a recursive solution, recursion is not really appropriate for these kinds of problems. Okay, let's now see how careless uses of recursion can lead to extremely inefficient programs, and while considering this, we'll also introduce analysis of programs for analyzing how much time a program takes to solve a given problem as a function of the size of the problem instance. And to do all that, let's consider the following problem as an example. You have to write a function to compute x to power n for given values of x and n. X can be a floating point number or an integer, it doesn't really matter, but n is a non-negative integer, that is, n is an integer which is greater than or equal to 0. Now, how do we compute x to power n? The naive simplest solution is start with 1 and keep multiplying the answer by x till you do it n times. So start with 1 and multiply it by x n times. So this obviously requires n multiplications, and the time taken by the algorithm would obviously be proportional to the number of times the multiplication operation is performed. Now, if we think a little bit about this problem, we'll find that we can actually do substantially better than n multiplications. So let's see how. Consider the following facts which all of us know about exponentiation. X to power 0 is 1 for any value of x. X to power 2n is the same as x to power n squared, and similarly x to power 2n plus 1 is equal to x times x to power n square. And we can use these facts to very easily come up with a efficient recursive solution to this problem of exponentiation. And to see what this algorithm will be, we have to simply utilize these properties that we just saw. If the exponent value that is given to us, that is the power that we have to raise x2, if it happens to be even, then what we can do is we can raise x2 half that power and then simply square the result. And if the power is odd, then we half the power obtain the result, square it, and then multiply by x. So that's what is happening in this case, and that can very easily lead to a recursive solution to this problem. We'll see the recursive solution in a little while, but let's try to analyze how many multiplications will be required if we do that. So let us say we denote the number of multiplications needed to compute x to power n in the worst case as Tn, where t is a function of n. Clearly the number of multiplications required will be a function of n, and we have to find what this function Tn is. So clearly you can see that T0 is 0 because x to power 0 is 1, and we can compute that without using any multiplications. And to compute Tn, what we need to do is compute to compute x to power n. What we need to compute is x to power n by 2 and then square it, and if n happen to be even, that's the answer, and if n happen to be odd, then we have to multiply it once again by x. So how many multiplications are needed? To obtain t to power n by 2, the time taken the number of multiplications would be t of n by 2. We are using floor because n by 2 would give us only the integer component, which will be the floor of n by 2 in general, and then we have to square that, so that's one more multiplication, and then possibly we have to multiply the result again by x. So in the worst case we require 2 more multiplications, and so t of n is t of n by 2 plus 2 for all values of n greater than equal to 1. So now this function t has been expressed as a recurrence relation, and we can actually easily solve this recurrence relation by keeping on expanding the terms t of n by 2, writing that in terms of t of n by 4, and so on and so forth. So let's do that exercise. So for n equal to 1, n greater than equal to 1, as we just saw, Tn is equal to t n by 2 plus 2, and then in the next step t of n by 2, using the same relation, we can write as t of n by 4 plus 2, and so that becomes t of n by 4 plus 2 times 2, and in the next step it becomes equal to t of n by 8 plus 3 times 2, and so on and so forth. So now in every step we are dividing n further by 2, and finally this value n by 2, 4, 8, 16, 32, etc., finally this value will become 1. And in how many steps will it become 1? See, we are dividing by 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. And so finally when we divide by 2 to the power log 2 times n, then this value will become 1. And so the point is that in that expression we'll get t1 plus 2, how many times? Log n times, the floor of log n times. And so t1 we of course know to be again Tn by the same relation is T0 plus 2, so we add 2 one more time, so finally the number of multiplications turns out to be 2 times the floor of log n plus 1. Note that this is a logarithmic function of n, whereas in the Naïve algorithm we had to perform n multiplications, which is a linear function of n, whereas using this square and multiply algorithm, we require only the number of multiplications required is only a multiple of the logarithm of n, and naturally for large values of n, the even 2 times logarithm of n is always going to be less than n. So that's how we analyze the running time of an algorithm, and in fact so essentially what we need to do is to find the running time of the algorithm in its worst case, because that is what we are usually interested in. So the worst case time taken is expressed as a function of the input or of the input size. So in this case we have expressed Tn, which is the number of multiplications, but really the running time of the algorithm would also be proportional to Tn. Note that we are not really bothered with the actual running time of the algorithm on a particular machine. On any given machine, the actual running time of a particular program will depend on so many factors, like how exactly the algorithm was implemented, and what was the compiler used, and how fast is the machine, how much memory it has, and so on and so forth. Number of factors which cannot really be analyzed very easily. But this notation gives us a way of analyzing the running time without really worrying about these constants. So that's the big O notation that we are going to talk about. So the running time, in the running time expression that we obtain using the kind of analysis that we just saw, usually the multiplicative constants are ignored because they would vary from different machine to different machine. So those are not really important, and we can't predict those constants really. And also the lower order terms are not so important for reasons that we'll just see. So in the previous example we saw that the running time is a constant times log n plus a constant. So both the value of the constant and the additive constant, both are really unimportant in the big O notation. So the big O notation is used to express the order of the time taken, or in general of any function. So in this particular example, the time taken by the square and multiply algorithm in the big O notation is order log n, which is written in this fashion, big O, and within brackets the function log n. And this informally means that the time taken is some constant times log n plus terms which are lower order than log n. Now the big O notation is very significant because it abstracts away the constants and the lower order terms. And it's important to understand that if the order of an algorithm is greater than that of another algorithm, so for example order n is greater than order log n, then the second algorithm, which has a smaller order, will always be faster than the first algorithm, which has a higher order, for large enough input values, regardless of the values of the constants and lower order terms involved. So for example, an order log n algorithm will always be faster than an order n algorithm for a large enough value of n. So what this means is that if you have an order log n algorithm, then the running time of the algorithm is some constant times log n plus lower order terms, and for the order n algorithm, the running time is some constant times n plus lower order terms. Now regardless of what these constants and the lower order terms are, we can always find a value of n beyond which the time taken by the order log n algorithm will be less than the time taken by the order n algorithm. So let's see this in terms, let's see this by plotting some of these functions. So this plot shows three curves. The blue curve plots 1000 times log x. So this is an order log x function. Note that the multiplicative constant is 1000. The pink curve is a linear function of x. It's 100 times x. Note that even though the constant is 10 times smaller in this case, but still the linear function, that is a straight line, always overtakes this log x curve. And this will be true regardless of what the relative, what the constants, what the magnitude of these constants are. And the third curve we have plotted is a parabola which is 5x square, and again the multiplicative constant is very small compared to the others, and it will also always overtake the linear, the straight line, as well as the log x curve, regardless of the relative magnitudes of the constants involved. And that's why when we talk about the running time of an algorithm or the complexity of an algorithm, we talk about really the asymptotic complexity, as it is called, where we talk about very large values of the input size. And for very large values of input size, as these curves show, the actual values of the constants and lower order terms are not really important. It's really the most dominating term or the greatest order term which is really important. That's what the big O notation really represents. Okay, but so we have got an efficient algorithm for exponentiation, but suppose we implement this algorithm in a recursive fashion as shown in this code. So x and n are given as parameters, and the function is if n is equal to 1, return 1, else if n is even, then return x to power n by 2 into x to power n by 2. Otherwise n is odd, and so we return x into x to power n by 2 into x to power n by 2. So this correctly computes the value of x to power n, but what is really wrong with this implementation? What is wrong with this implementation is that we are computing the same value twice. So if you look at, for example, this statement, we are computing x to power n by 2 once here, and then we are again calling the same function recursively with the same parameters once again. So we are recomputing x to power n by 2. So this is obviously inefficient because we needed to compute this value just once, and then we could have reused this value to multiply it with itself. So what we have seen is that x to power n by 2 is being computed twice. Now for each computation of x to power n by 2, we'll have to compute x to power n by 4 twice, which means overall x to power n by 4 will be computed 4 times. And similarly, x to power n by 8 will get computed 8 times, x to power n by 16 will get computed 16 times, and so on and so forth. So clearly this is extremely inefficient. Let's see precisely how inefficient it is by trying to analyze the time taken by this particular implementation. So let's denote the time taken to be Tn for where n is the exponent. So when n is 0, clearly the time taken is a constant, some constant C1, and for n greater than 0, Tn is 2 times t of n by 2, because we are calling the function power x n by 2 twice, plus a constant, and so this constant would be the time taken to multiply x into the power of x to power n by 2 into x to power n by 2, and so on and so forth. So as I said, the actual values of the constant C1 and C2 are not really important. So what has changed from the previous reconciliation? In the previous reconciliation, this factor of 2 was not present. But because this factor 2 has come, suddenly this the time taken by this algorithm has gone back from being a logarithmic function of x of n to a linear function of n. So I'll leave it as an exercise for you to show that Tn is actually order n. So this is not really a good implementation of the square and multiply algorithm. The algorithm is good, but we have not really implemented it properly. We have not used recursion carefully enough. And if we really want to get the benefit of the speed up that the square and multiply algorithm offers us, then we have to make sure that we from within a function we make only one recursive call to the function and reuse the return value. So that's quite easy to do. So here what we are doing is, if n is even, we call power again to compute x to power n by 2 and save the return value in a variable t, and then multiply t by t to compute x to power n by 2 times x to power n by 2. And similarly, if n is odd, we save x to power n by 2 in a variable t and then compute x times t times t. So there are in this function still there are two calls to the power function, but for a given value of n, it is easy to see that either this call will be made or this call will be made. Both of them cannot be simultaneously made, because clearly n can be either even or odd, it can't be both. Of course, we could have called power somewhere outside this if statement in both the cases at a common place, and then use that value in both these, but that would not really have been any different. So this particular implementation of the power function now actually correctly and efficiently implements the square and multiply algorithm for exponentiation, and it does give the speed up benefit and has a running time of order log n. Okay, let's now take another example to see how recursion should not be used. So let's consider the computation of Fibonacci numbers. The Fibonacci series is defined as follows: f of 0 is 0, f of 1 is 1, and for n greater than 1, f of n is f of n minus 1 plus f of n minus 2. So essentially, any term in the series is the sum of the last two terms. Now suppose you want to write a function to compute the nth Fibonacci number, that is to compute f of n. You can see that we can write a very simple iterative algorithm to compute f of n. All we have to do is we have to remember the last two terms in the series and keep adding the last two terms to obtain the next term, and in the next iteration the newly obtained term and the last term become the last two terms, and we keep doing this till we have obtained Fn. So here is the implementation of the simple iterative algorithm that we discussed just now. Cur and Prev are the last two terms that have been computed in the Fibonacci series, and we always maintain I such that Cur is f of I and Prev is f of I minus 1. So if n is equal to 0, we return 0. Otherwise, as long as n is greater than I, that means we have not yet computed f of n, because the last term that we computed was f of I. So we add up the two terms, and that becomes the new value of Cur, and the value of previous is the old value of Cur, which we saved in t and then assigned it later to previous, and then we increment I, because now one more term in the series has been computed. And finally, when n becomes equal to I, we return the value of Cur, because that will be the value of f of n. Now, so that's simple enough, but looking at this recurrence relation, one might be tempted to implement the algorithm recursively by just adding up the values of f of n minus 1 and f of n minus 2 and use recursion to compute these two values, and we'll just see that that would be extremely inefficient. But let's first analyze the iterative algorithm that we just wrote and see how much time it takes. So note that each iteration of this loop takes a constant amount of time. It doesn't really depend on the value of n, and the number of iterations is n minus 1, and so therefore the total time taken by this function is order n, where n is the parameter supplied to the function. So let us say we write that straightforward naive recursive function to implement Fibonacci. So this is easy to write, but as it turns out, it's extremely inefficient, and we'll see why it is inefficient. So if n is equal to 0 or 1, we return the value of n, because f of 0 is 0 and f of n is 1. Otherwise, this function simply makes two recursive calls to itself, computes Fibonacci of n minus 1 and the Fibonacci of n minus 2, and returns their sum. Now, why is this implementation really inefficient? This is inefficient because the same values are again being computed multiple times. F of n minus 1 is computed only once, but f of n minus 2 is computed twice, because when f of n is called, it calls f of n minus 1 and f of n minus 2, and f of n minus 1 again calls f of n minus 2 and f of n minus 3. So if we try to see how the recursive calls to f are happening, we see that f of n calls f of n minus 1 and f of n minus 2, and this calls again f of n minus 2 and f of n minus 3, and this calls f of n minus 3 and f of n minus 4. So you see that f of n minus 2 is being called twice, and f of n minus 3 will actually get called 3 times, because f of n minus 2 will again call f of n minus 3. So f of n minus 3 is called once here, and once here. And if you look at f of n minus 4, that will be actually called 5 times, because it will be called from here, and it will be called from here, it will be called from here, from here, and from here. And so as the value of I increases, f of n minus I is called an increasing number of times. So this is obviously grossly inefficient, and if we write a recurrence relation to understand the time taken by this implementation, we'll find that for n equal to 0 and n equal to 1, clearly the time taken is a constant, but for n greater than 1, Tn is t of n minus 1 plus t of n minus 2 plus a constant. We'll not try to mathematically solve this recurrence relation, but it can be shown that t of n is actually order a constant raised to the power of n. So what that means is that the time taken by this algorithm, by this implementation of the Fibonacci series computation, the time taken grows exponentially as a function of n rather than as a linear function of n, as in the case of the simple iterative solution. So that's extremely inefficient. So this is the end of today's lecture. In the next lecture we'll talk about a couple of very important and frequently encountered problems. These are the problems of searching and sorting, and we'll try to develop some simple algorithms to solve these problems and try to analyze these algorithms to find their time complexity.